And we are live. Sorry if you have to listen to the sound of me drinking a bit, but my voice is a bit dry. Anyway, thank you for watching this stream on C. I'm going to be taking you through some C today, but before we get started, if you're watching on YouTube, there's a link in the description for a zip file you can download which has all of today's code as well as the challenge at the end, which might be useful. If you're watching on Open Learning, there's download links below as well. Now, I'm assuming that everyone who's watching this has already prepped their computer and has Clang installed and has run the test compile to make sure everything works. So, without further ado, we shall get started. I will disappear. So, in this course, we're going to be discussing a few different things split over 3 sessions. In this session, I'm just going to briefly describe what C is, show you a simple C program, show you how the main function works. We're going to do some arithmetic. We're going to do some compiling, so compiling some basic programs. We're going to look at the different basic types in C for storing numbers and numeric data. We're going to look at decision making based on inputs. So we're using if-else to do some branching. We're going to be displaying text and accepting user input. But up first is, what is C? The C programming language is a programming language written by Dennis Ritchie several decades ago, which was eventually used to write off the Unix operating system with, and is now used to write the majority of the parts of Linux, Apple OS X, or Mac OS, as it is now called, and Windows. And that book that you can see there, or this book here, is certainly recommended reading. If you don't have a copy, I would strongly suggest getting your hands on one. It is very useful, and if you're auditing C code or you're learning C, it's a great reference. If you see someone else's C code, you can pull it apart and have a better understanding if they're using more obscure things that aren't covered here or in standard C courses. Also, learn to use the internet, I guess. But yes, C was written as a programming language written a few decades ago by Dennis Ritchie. Prior to C, most programming was either done directly in machine code, which is the code that processors can read because they don't understand instructions written in English. They understand instructions that are just sequences of numbers, and each number relates to a specific instruction that it performs. So the number 90 might be just do nothing. We might have a number that's add 2 values together, and then that's followed by the 2 things to add together, or a number which represents an instruction to move things back and forth. And what this machine code looked like was just these numbers that you see here, and processors still use this machine code. It hasn't gone away. In order to make it easier to write with that, though, we have assembly, which just means that we can use words that then get translated into the numbers that the computer understands, but it's like a direct translation. So we have one word, which is basically a pseudonym for a number, which is an instruction. And so prior to languages like C, you had to write all of your programs which the processor ran directly in this assembly or machine code, and any programs that you had running in English, you had to write a program to interpret them. So that would be written in C, and in this machine code, and then that program would read through like your Fortran or your BASIC, and it would run the instructions that are written there in a more easy to read language. What C did was what it was designed to do was allow you to write a program in a fairly easy readable language that could then be translated to this machine code through a process we call compiling, which made things a lot easier. It allowed us to make more complex programs that got translated into this much faster to run machine code. But in order for it to do that fairly easily, the way it handles certain types of data is it handles them in a very dumb way, because it just basically passes them around through the processor, and the processor doesn't understand a lot about what's going on with them. And we'll see that a bit later on. And the way C does this translation is, say we have this function here, which is written in C. We would compile that with a program called a compiler, which is also now written in C. And it would take this function, which has two numbers as arguments. It takes the number 12, it adds the first one, it subtracts the second one, and it gives that number back. And it turns it into this machine code you saw earlier. They are actually the same function. It's just these are the instructions that the processor understands. And as you can see, the C code at the top is a lot easier to comprehend than this down the bottom. So we have C programs. And C programs are split up into a lot of parts. You have comments, which are littered throughout the program, but just help anyone who's reading through it understand it better. And those aren't actual code, those aren't executed. You have references to other files with the include statement there, which just takes the contents of another file and dumps it in yours, so that you can have one file that may have some content that's needed across a whole bunch of others. You have constants, which define a constant that appears multiple times throughout the file, like a piece of text or a particular number, and you can name that and have it occur all over the place, and it means that there's only a single place you have to modify it. And then you have your functions. And the only one we'll be looking at today is the main function. We'll be going into more functions tomorrow in detail. But this main function here just prints the text hello world, and then tells whatever part of the operating system ran it that it exited without anything going wrong. So as you saw comments in the last section, comments can either take the form of having two forward slashes, and then anything on that line of text that falls after those forward slashes is considered a comment and is not compiled. You can also have comments that are surrounded by, that start with / asterisk and end with asterisk / and anything between those two, even across multiple lines, is considered a function, is considered a comment. So you can see these comments here help us figure out what these functions do or what this variable is used for. And when we have multi-line comments, we like to use the stars with extra stars down the side, because it lines everything up nicely and it makes it a bit easier to read. Let me know if I'm speaking too fast. Just remember that if you are watching this on YouTube live, there's a live chat section on the YouTube page. Feel free to post any questions you have there, or if I'm speaking too fast, post their comments for me to slow down. I won't take kindly to comments telling me to shut up altogether, though. So, as I said before, we have references to other files. There's two ways you can do this. You have include, and then with the angle brackets, they include files from the standard library or that have been named elsewhere that describe functions that other libraries provide. So this string.h file won't have the functions themselves, but it will just have enough code in there to describe how those functions can be used. So it describes functions like printer. It describes functions like string comp, which allows us to take two strings and compare them and see if they're the same, or if one would fall before another alphabetically or whatnot. We can do similar things with our own files. So if we have our own file that has some code that appears frequently across a number of programs or files, etc., we can use double quotation marks to have a file that's in the same directory as our program dumped in the middle of another. Functions, the only function we'll be looking at today is the main function. Now the main function takes two main forms. It returns a number, which is why it's int main. So we say type it returns, the name of the function, in this case main, and then all of its arguments, or void if there are no arguments. And throughout this section, we'll only be using the first form there. These second two forms are all pretty much the same. They're just two slightly different ways that you'll see littered across the place. But main returns a number once it's finished. That's why it's int. And then we have return 0 or return exit success. And the way that works is the number that main returns tells whatever ran the program how it went. So if it returns a 0, that means that everything went fine. It's hunky-dory. If it returns any other number, that indicates that there was an error, something went wrong. And what number that was usually indicates more precisely what went wrong. And then in main, you have all of your code, you have calls to other functions, everything happens in there. So every complete program in C must have that main function to work, because that is what gets called first. So in order to store data whilst our programs are working on it, we use variables. Variables take a section of computer memory and say, I'm going to use that section of memory to store some data. Depending on the type of that variable, determines how much data is used to store that, how much memory and bytes is used to store that data, and how it's arranged there. So we can have standard integer types, which store whole numbers, and they can be signed, in that they store both positive and negative numbers, or unsigned, in that they only store positive numbers. And we have a few different sizes of these integer types. We have the char, which is the smallest, the short, which is the next smallest, the int, which is the one that we use a lot of the time. It's a good multi-purpose integer type, but it does have its constraints, notably its size. So there are larger ones. We have long int and long int, and there are unsigned variants of all of these. So variants that store the larger positive numbers but no negative numbers. And if you need to store fractional numbers, like we refer to as floating point types, we have the float and the double, which is twice as big as a float and is roughly twice as precise. There's also something referred to as a long double, which is slightly more precise than a double, and it can just hold a few more decimal places. And as you can see, the way we declare a variable, we say what a variable is. We say, I'm going to have a variable called tiny number. And the name can only be letters, numbers. It must start with the letter. It can only contain letters and numbers and underscores. And it's case sensitive. So if I had tiny number with a small n in the middle, that would be a different variable to tiny number with a big N in the middle. And then the compiler will find some area in memory and figure out how to store our data there. And we'll go into that more into how that happens next session. For this session, it's just somewhere in memory, but we can refer to it using its name. And then we have literals. Literals are where we just have literal versions of numbers in our code. So if we want the number 64 to be stored in a variable, we can assign it using the equals symbol and the literal 64. But there's a few different flavors of literals. There's integer literals, so we have decimal, which is base 10. We have octal, which is base 8, and this octal number is actually incorrect. It should be 0100. But when the compiler sees any literal that starts with a 0, it's assumed to be base 8, so it should only be digits 0 to 7. And then we have hexadecimal, which is digits 0 to 9, and then A, B, C, D, E, and F. And the reason we have hexadecimal is very useful, and you'll probably see it a lot, is that it makes it very easy to write like directly the binary of what a particular value should be. Noting also that octal values and hexadecimal values can't be expressed as negative. Only the decimal ones can. The way we store characters and things to be written to the screen in C is actually just using numbers. Using the numbers for the ASCII values of things. So in order to get the ASCII value of a character, you don't even need to remember it. You can just put, say, the character capital A in single quotes, the single quotes being rather important. And that will automatically translate it to that number value for that character. So that's useful. Real numbers or floating point numbers, of course, you just write with a decimal point. And string literals are in double quotation marks. So it's important not to mix up single quotation marks, which are for characters, and strings, which are double quotation marks. We won't go into strings and how they work this session. That'll be the next session. But just keep that in mind for now. We will use some string literals. We won't look at how they're stored just yet. And compiling is actually pretty easy. So we have a compiler called Clang in this case. You might also know GCC. But you can just type Clang as the command in Linux. I think Windows, if you've set it up properly, you can also just type Clang. And then after that, this is in your command line or your terminal. After that, you can just give it some options. So the options we like to give it is $W all, which means show me every single warning you can. Any slight thing I did wrong, let me know. I want this program to be perfect. Then after that, we do $W error, which means any of those warnings you showed me, make them errors. Don't let me compile a program if any of them show up, which means we make sure that no errors that the compiler knows of are going to get into our program. We then have -O, and whatever we want the resulting program to be called, then we can just type the names of the files that we want the compiler to translate into machine code, or pack them all together and put them in a file called, in this case, my program, which we can run. And in order to run it, we just say // and the name of the program we wanted. And because this is the program that I showed earlier here, all it's going to do is print hello world. So it prints hello world, and that's it. So, getting into some more heavy stuff, some simple arithmetic, some simple arithmetic. So the first thing you generally need to be able to do with variables is store data in them, and that's done with a single equals sign, with the variable you want to store data in on the left, and the data you want to store on the right. And that data may be like a literal number, it may be another variable that we're getting. I believe -wall is literally all. At least in the case of Clang. I may be incorrect though. But yes, back to this. So what's on the right may be a single literal, like the numbers you see up there, but they can also be complex statements of mathematics and arithmetic, or function calls that result in numbers. But any expression, as we would say, that can be evaluated to a number that can be stored in the variable. So say there's a number 3 is stored in variable p here, we can store whatever's in variable b plus 5, which is 8. In variable d, we can also use, in the third block down here, we can use these operators to modify the variable value that's already in a variable. So we can add 1 with plus equals 1. We can multiply what's already in there by 8 with times equals 8, and so forth. We also, right at the bottom here, have incrementers and decrementers. I won't go into too much detail about how these work right now, but I will recommend that you look into them shortly. It's very important to note that the way these work depends on whether the double plus or double minus comes before the name of the variable or after it. It's very easy to get confused there. But a double plus will always increment the value in the variable by 1. A double minus will always subtract 1. And then there's calling functions. And calling functions simply work by typing in the name of the function, and then in brackets, well, apparently -w extra. All right, but yeah, in between the brackets, you have the arguments. So for printf, it takes a string literal with some special stuff in there to tell it how to display some the rest of its variables, arguments, and then you put the arguments in afterwards that you want it to display. As you can see here, the first one will print out your number was 79, and the second one will print out your number is 4f, because we can print it in hexadecimal as well. And with that, Wow. So, to correct a previous error that I made, when you use -w all here, it doesn't do all errors, it just does most of them. There are errors that it doesn't check for here that you can add extra options to check for, but we won't go into that right now. This does cover a lot of things though. Just to clarify that that particular issue there. But now we have enough to make a basic program. Clear and clear. So we're going to start by opening up Nano, and we'll just make it simple.c. So that's going to make a file that's just simple.c, and we end all our C programs in .c. So the first thing I'm going to do, because I like to know what I'm doing, is make a comment up here. I'm just going to say what the name of the file is in case the file ever gets its name changed for some reason. I'm going to give a description of what it does. Some simple arithmetic with C. Make sure we know who wrote it. Make sure we know when it was written. Make sure we can spell. And the comment. Nano's nice, and it just highlights all that as a comment for us. Then I need to reference stdlib so I can get some standard library stuff. In this case, the only thing we're using from stdlib is the constant exit success, which you will see later. And then I have stdio, which lets us use the function printf. We'll just use the void form of main here. We'll make sure we return something at the end. There's no way this program's going to have an error and balk. So what we're going to do here is we're going to make... Well, I said that we have different types that store different size numbers, but we're only going to be dealing with small numbers here, so surely we can get away with just a char, because that still stores numbers. I'm just going to call it variable. We're going to set it to 2. So this is what I'd say is initializing the variable, is where we declare the variable, say that it exists, what its type is, and give it an initial value, so it starts off with some data in there rather than some random stuff that was just whatever happened to be in the memory that was assigned for this variable. And I'm just going to say print f variable. Because it's a char, I can't just say %d because that expects it to be an int. But I can say HH, which is like super short. H is for short. D. N. And then I say variable. So where HHD is, it's just going to give me the value that's in variable. So that should just print 2 at the moment. So let's save that. So Control O, Enter, Control X. So we can go clang, wall, where O, simple.c. And that compiles. So now I can run simple. And it says variable is 2. Alright, let's try and do something a bit more complicated. Let's try and do some addition. Variable. Now because I've already said what the type is here, I don't need to say the type again, it knows the type. So I can just say variable. Variable equals 7 plus 12. Then we'll print it out again. Alright. Let's save that. Compile it again. So variable 19. Okay, this is looking good. Looking pretty straightforward. Let's try and do some subtraction. Let's see if we can get a negative number out of this. Variable equals 8 minus 120. Let's see if that breaks it. I highly advise having the attitude of trying to break any program you try and write. It makes it easier to spot bugs. If you're wondering what I'm doing here, I'm just using cut and uncut to copy and paste. So that's Control K to cut and Control U to uncut, and then you can uncut multiple times to paste. Control O to save, Control X to quit, compile it again, run it again. 112, we can do negative numbers. All right. Let's try that subtraction thing I showed as well. This is getting very complicated, isn't it? So variable, let's try and modify the number that's already in there. So we go minus equals, and we're going to, so that was 112. Let's subtract 40. So it should be 152 now. So cut, uncut, we go down here, uncut again. So we should get 152, if, negative 152 if we're subtracting. Let's compile again. There we go. Oh, it's 104. Maybe our computer just messed up. Well, let's save some time. Here's a different version I prepared earlier, which is also in the zip file. So what we're going to do now is we're going to get another variable, but this time it's going to be of size int. So this variable here, after this, should be 152, but it's not. So we're going to store it in the bigger variable and see if that makes a difference. And then we're going to try and do the same maths again. So we'll get it down to negative 112 and subtract 40 again and see if the bigger variable, which is an int, has any issues with that. So we're going to close that. We're going to compile it. Clang, wall, where maths, maths.c. Gonna run maths. So the int gives us a negative 152, but the first variable, which was a char, only gave us 104. All right, let's see what's going on here. So, computer memory. I said that when you make a variable, it picks a spot in computer memory. It has a very specific way of picking such a spot, but it picks a spot in computer memory to store that data in. So if we look at computer memory, this isn't how it looks on a chip, but so computer memory is split up into bytes. Each is 8 bits. Which is standard, and that byte is the smallest amount of memory we can access in one go. We can't really split it up any smaller. Processors also have what is known as a word, which is what it normally operates in, the size of data it normally operates in. So for a 32-bit system, as you could probably calculate from the name 32 bits, has 4-byte words, so that's 4 8-bit bytes to make 32-bit word, and it does all of its calculations in those 32-bit words. For a 64-bit system, it has 8-byte words. So you can see the top here is our 32-bit system. I've drawn it here, so it's 1 long, and we go from 0 all the way to the bottom. And each of these bytes we can actually refer to individually with a number. And the way that number works is it's the distance, essentially, the number of bytes it is from the first one. So because the first one is the first byte in memory, we refer to that with the number 0, because the second byte is 1 away from the first byte. It's 1. The second is 2 away from the first byte, so it's the third is 2 away from the first byte, so it's 3. So that's why. So you'll see that sort of thing happen a lot. Is when we're dealing with lists of things or arrays of things, the first one will be 0, the second will be 1, so on and so forth. We'll refer to that as being 0 indexed. But that's the way we refer to our memory, and so we can use numbers. As you can see, they're written in hexadecimal here, and we'll look at hexadecimal a bit later, but we can use a number to refer to any of these bytes in memory. And I said each of those different types had a different size as well. So the char we were using tends to only be 1 byte big. There's only so much data you can stick in 1 byte. In fact, if you assume that you're only storing positive numbers in that 1 byte, you can store all of the numbers from 0 to 255. If we're going to put in negative numbers, then we can't store that many positive numbers. So generally for a negative number, we can only store negative 128 up to 127, which is why when we tried to store the number negative 152, it didn't work. It can't store that number. It can't record that number in a single byte. And so it looped around to the positive numbers and became positive 104. As to overcome that, we tried to do the same thing with an int, which uses 4 times as much space, which stores much bigger numbers, and so it did not have any troubles with the number negative 152. But so the different types we have is char is usually 1 byte, short is usually 2 bytes, an int is usually 4 bytes. I say usually because it does depend on the system you're working on. A long int is usually 8 bytes. A long int, however, is usually a word. So on a 32-bit system, a long int will be 4 bytes. On a 64-bit system, like most of you should be using, it will be 8, which is something you have to watch out for because it might behave differently depending on what computer you're running in. Floats are always 4 bits, and doubles are always 8 bits, because there is a very particular way in which data is stored in them so that we get decimal points. And there is also a thing known as a long double, which is slightly more bits than a double, but it's not very specific on how that's stored. And then we have another type, so when we want to refer to a particular byte in memory, we use what's called a pointer, and that has to be the same size as 1 word. And that's used to store a number that refers to a particular byte in memory. We refer to that as pointers. You can also use this size of functions, or sort of function thing, on any type or variable to tell you how many bytes it's using in memory. And as you can see, this is 64-bit, so you can see the size of most things have changed. The words are twice as big, but long int is now 8 bytes instead of 4, like it was up here. Printf. Printf is a wonderful function. It lets us print wonderful things. You can get printf to not only print you decimal numbers, so that's base 10, but you can get it to print octal numbers, which is base 8, which is only the numbers from 1 digits through 0 through 7. You can get it to print hexadecimal, which is very handy, as I'll demonstrate in a minute. And you can even get it to print numbers as ASCII characters, which is, so as you can see, %d prints a decimal number, %o prints an octal number. We say prints, it's not actually doing anything with paper, it's displaying it on a screen, but we say prints because Dennis Ritchie, I guess, decided that's what we do. We have %x for hexadecimal. %X does hexadecimal, but it uses capital A, B, C, D, E, and F rather than lowercase. If we're using different types with printf, we need to tell printf what type it is. So if it's a long int, we say LL, and then whatever we want it to print. If it's a long int, we say L, and then the way we want it to print. H for short and double H for char. And as I said, so you can see up here, this has its value as a hexadecimal literal. And the reason it's very useful to be able to write hexadecimal literals and read hexadecimal literals is because it's very easy to write binary data with just hex, because binary values can be split up into groups of 4 bits, and each 4 bits in binary can be translated directly to a single character in hex, which means we can use a quarter of the space to represent the same value. And it's very useful to be able to convert directly from binary to hex. And as you can see, there's a table here to help out. So I'm not going to leave this table on the screen for too long. You have access to the slides if you want to check it out. But I would be familiar with that if I were you. And then if we're doing printing floating point numbers, we use %f or %lf for doubles to print them as floating or real numbers there. If you want to print in exponent form or scientific form, you can use E on a float or LE on a double, and you can see how that displays down there. And there are other ways you can modify the way that output is used. You can add numbers in order to change how much space is used to print it. You can add you can put multiple things in a printf statement so it prints out multiple variables or numbers. You can use a hash at the start of the format token thing for hexadecimal and octal for it to add the 0x or the 0 automatically, so it looks like hexadecimal and octal. I'm not going to say absolutely everything here, but what I will demonstrate is that if you have Linux installed, like you should, or this works in OS X for the most part, you can use the man commands. If I say man, 3 is for C library functions, and if I just type in printf, this gives me a whole manual, which I can navigate with my arrow keys, on how to use printf. This works for most C functions as well. So yeah, the reason, printf is so named because of the way we used to work with displaying text. There are many and varying ways in which that would work. Now it's all screens. But yes, you can figure out how to use printf and all the different ways you can augment those tokens here. And if you need to print a percent sign, just double %, we'll print a single one. So if you need to find more about printf, use the man page. All right. And you can also print hard to, you can use not just in printf, but in any string. If you need to describe hard to display characters that you can't easily just put straight into a string literal without it being obvious. And these can also work inside the single quotes just to get their character values, because they are actual characters. You can use escapes for like new lines, which is \n for Linux and OS X to have text appear on the next line under, or \r\n on Windows. You can use \t to have tabs. If you know the octal value or the hex value for a particular character in ASCII, you can use / and then the octal or \x and then the hexadecimal to put that in. You shouldn't be confused with the decimal value. You can't use the decimal value there. It assumes it's octal. And in order to put in backslashes, you use double \. In order to put in quotation marks so that it doesn't end the string literal, you use \, quotation marks, etc. Now that we have all of this wonderful magical stuff we can do with printf, and we know all of these quirky things that happen with types, we can try and figure out what exactly was going on with our program before. So when I ran maths, the variable that was a char didn't work out so well, but the variable that was an int did all of the maths just fine. So in order to fiddle around with some types, I've made a program here called type double, which is also in the zip file, so you can check it out and read it. So let's take a look at that. So what this is going to do is I've picked some very particular values, which we would refer to as edge cases, because the way that these particular numbers and numbers around them operate can cause some odd behavior because of the way that C deals with types, deals with some values. And I said it deals with them in a very dumb way, and you're going to realize why I describe it as dumb pretty soon. It doesn't do anything intelligent to mitigate certain things going wrong. So what it's going to do is I've given each of these a very particular value. It's going to tell us what that type is, how many bytes it's using to store data. It's then going to print out in decimal what the value stored in that variable is, and then it's going to print it in hexadecimal. The reason why I'm showing you in hexadecimal should be apparent very soon. Then it's going to double it. It's going to print out decimal value in hexadecimal again. Then it will double it again, print out decimal and hexadecimal again. And it's going to do this for a char, a short, an int, and a long int using those particular values. So that's just a shortcut I can use to compile that. So if I run type double, you see for the char at the top starts off at a value of 64. Then we double it, and it doubles to negative 128, which is odd, because double 100, positive 64 should be positive 128. And then we double negative 128 again, and it becomes 0. Useful. And you can see that 4, 0, and 8, 0, and 0 there. There's so a similar value on here. You can see that the numbers we're getting in hex have a similar effect on a short, which is 2 bytes. On an int, which is 4 bytes, there's similar values which produce a similar result, and the same with a long int. And I'll try and demonstrate exactly what's going on here, but have a play with this code if you've got it. So I'll move over to my pseudo whiteboard here. So the way we represent numbers in binary, let's say we have an imaginary half byte type, which is only 4 bits long. And I'm going to put the number, where's my pen? I'm going to put the number 0, 1, 0, 0 in there, which in decimal, as I'm sure we all know, is equal to 4. If we go back here, you can see that 4 was the number, was the one of the numbers we were using in binary here. So if I double 4, let's do some long multiplication. What's 2 in binary? That's 0, 0, 1, 0. All that does is really make it 1, 0, 0, 0, which, if we assume this is a positive number, is 8. And we should get 8. But what actually happens is we have 2's complement, which is a way of storing negative values that computers use. The way we calculate what any number is in 2's complement is we can generally ignore it if the highest order bit, as we would call it, is a 0. Then we assume it's just positive, that value. For this value, the highest order bit is a 1. So in order to figure out what value that has, we will subtract 1, which gives us 0, 1, 1, 1. And then we will flip all of the bits, which gives us 0, 1, 0, 0, 0. May not look so useful yet, but this now tells us what the negative value is, which is negative 8. To make this a bit simpler, let's try it with a smaller number. Let's try it with the number 2. Let's try it with the number negative 2, which is going to be 1, 1, 1, 0. Might seem a bit intuitive. You'd think, wouldn't that be negative 1? No. So the reason we have the minus 1 is for a few reasons. But well, minus 1, which will give us 1, 1, 0, 1. We invert it, we get 0, 0, 1, 0, which is 2. So that's negative 2. The reason we have 2's complement is so that for increasing binary, increasing binary values, so we have 1, 0, 0 equals negative 8, 1, 0, 0, 1. So if we increase that, we still get an increasing number. Negative 7, 1, 0, 1, 0, negative 6, so forth. So this is what's referred to as an overflow or underflow error. And it means that we're trying to move beyond the ability of what that type can hold. And so it just loops back around on itself with the arithmetic. So that's what's been happening there. So when we have the number 0x40, which is 0, 1, 0, 0, 0, 0, 0, 0, we multiply that by 2. We get this number, which if we do our 2's complement maths on it, is equal to negative 128. That's equal to 64. And then if we multiply it by 2 again, this is where C becomes really dumb. So if we multiply that by 2 again, we would get 1, 0, 0, 0, 0, 0, 0, 0, 0, but we only have a byte in which we can store this data. So we get rid of this 1 up here, and we're left with just the zeros. So that ends up being 0. So if we go back here, we can see that we got 64, then it became negative 128, like it did over here. And then we doubled negative 128, and we got 0. So you have to be very mindful of how dumb C is when it works with numbers, because it can lead to some unexpected errors. All right, and that will happen for different numbers, but in a similar manner, depending on how much space you're using for those types. So now another thing we might want to be able to do is instead of using the same numbers every time we run a program, get some way of reading in numbers from the external world, perhaps by having someone type them in. And we can use scanf to do this, and this uses similar format strings to printf, except one thing we must be mindful not to do with scanf is put a -n at the end like we would with printf. With printf, putting a -n at the end means that what's printed next doesn't get printed off on the same line, or displayed on the same line. Scanf will expect us to input a new line when it's looking for stuff we're typing in, which scanf throws away, so it gets a bit fiddly, but don't accidentally put a \n in your scanf, otherwise you'll find that it won't work like this bottom one down the bottom. But yeah, scanf, you can scan in multiple variables. Another thing with scanf is, in order to allow it to modify the variables that are in our function, we need to put an ampersand in front of them, which instead of just saying what number the variable holds and giving that to scanf, it says this is the address where this variable is, and scanf will say, I'm going to take that address and I'm going to change the number that's stored there. Another thing that we might want to be able to do is change what we're doing based on some conditions. So if something is equal to true, we might want to run one set of instructions. And if it's not, we might just not want to run those instructions, or we might have separate things that we want to do. And we can do that with if-else statements. The way the concept of true works in C is also a bit fiddly, because it has to be stupid about it. Any number can be considered either true or false. C uses numbers to evaluate true and false. Any number that is 0, or any variable that evaluates to 0, or any expression that evaluates to 0 is considered false. Any expression that evaluates to any other number, 1, 20, 53, -12, they're all considered true. So you have to be very careful about what expressions you're using, your if statements. Try to make it as clear as possible. So in order to help us with our if statements, we also have operators that allow us to do comparison. We can do comparison between values stored in variables, constants, and so forth. We can do less than with the obvious less than sign. We can do check if two values are equal, but we have to use double equals in this case, so as to differentiate it from trying to assign a number to a variable. So double equals will be equal to 0 if they're not equal, in this case, or 1 if they are. Less than, which does 1 if the first thing is smaller than the second. Less than or equal to. For not equal to, we have exclamation mark equals. This means so in the case here for test 5, we have 3 exclamation mark equals 4. So 3 is not equal to 4, which is true. We can invert the truthness of an expression with the exclamation mark. So we do 3 is not equal to 4, but we use the exclamation mark to say not, which makes it from true to false. And because any number can be can be considered true or false, we can just use an exclamation mark in front of a variable to invert its true or falseness. And then, as you can see down in test A there, if you use 2 exclamation marks, the first exclamation mark will take that number. If it's 0, it will make it 1, because it'll go from false to true. And if it's any other number, it'll make it 0, so it'll go from true to false. And the second exclamation mark will reverse that and ensure that that variable is that value is only 1 or 0 for true or false, which is something you might see pop up all over the place. And then there are ways that we can chain these tests of truthness, or these comparisons together using AND. So as you can see, the AND test down the bottom uses double ampersand. A single ampersand does something different. There's a few somethings different, but double ampersand to chain two comparisons together, or two true or false statements together. And if they are both true, then it is true. If either of them is false, then it is false. Then you have OR, which is if either of them are true, then the whole thing is considered true. And if neither of them are true, then it is considered false. Right. It may not seem like we've got through much today, but we can now respond to user input. So, let's make a simple guessing game. Nano game.c. So we'll make our comment up here. We're going to need standard lib. Going to need standard IO. Going to need our main. We're also going to do some Boolean logic here. So I'm going to define two constants. I'm going to define false as being 0. Then I'm going to define true as being not false, because I find that easier to remember personally. That'll make sure our true value is certainly true. And we have int main void, and this is going to be our main function, which is the heart of the program. I'm going to declare an int, which is going to be the number to guess. Let's make it 53. I'm going to have int here, which is going to be what the user guesses. So we're going to ask for them to guess. We'll make it 0 to begin with. And then, in order to store whether or not they've guessed correctly, we're going to have something here which is just false. So we'll say printf I am thinking of a number. Guess what it is. And then we'll get them to guess. Or, keeping in mind that scanf does not display any text, so do not confuse scanf for displaying text. If you want to have something to display text before someone types something in, you have to use printf or similar. Enter your guess. And I'm not going to put a dash n at the end because I want the person to type on the same line. Then I can get their guess with scanf. I want to get it as an int, so that's %d, just like you would for printf. I say ampersand guess, so that it knows where guess is to store it in. Then I can use my if statements. I can say if guess is less than 2 guess. I'm going to tell them that they need to guess higher. Higher. And I can chain if statements together. I can say else if guess is less than. So if it wasn't less than, we'll say, well, if it's greater than. Printf lower. So you should guess lower. And then if neither of those are true, then surely they have to be correct. And then I'll say guessed is true. Why I'm doing that will become apparent in mere moments. Turn, exit, success. Wall, where game.c. made a mistake. So this is saying I forgot to add the equal sign here. Save it, exit. Now I can run game. So I'm going to guess 12 and it says higher. I guess 70, it says lower. I don't want to have to run this game every time I need to make a new guess. So what I've done is here's another I've prepared earlier. This version is very similar, except it uses that guessed thing to say if you still haven't guessed it 2 more times, it gives you another chance to guess. So I can stack, wrap if statements inside other ones as many times as I like. Don't go crazy with this, though it makes it hard to read. So you can check this out. This, like the other function, like the other programs, is in the zip file. So if I make run guessing, this has a different number though. So if I go 120, it's going to say I need to go higher. If I do 140, I need to go even higher. If I do 200, it says incorrect. Let's see if I can break this though. As I did say, we should try and break these things. I wonder what happens if I change int to unsigned. Save that. Is it going to make much of a difference? Compile it again, run it again. Let's do 20. It says I need to go higher. Let's do 160. Higher. 170. Incorrect. So I do -1. I need to... It's odd. I need to be both lower than -1 and higher than 2. Maybe I broke something. Maybe I shouldn't have made it unsigned. Maybe this is more of C being dumb. Let's take a look at this. Ah, yes. So because I have both an int and an unsigned int, and I'm comparing the two of them, as you can see here, guess and toGuess are being compared. They're of different types. I have to make them the same type so I can compare them. So what C does is it says, well, these are both 8 bytes long, but I think that the unsigned one has more information, so I'll make you both unsigned. And how do you make a type that's signed become unsigned? Well, it's easy. You just start assuming that it's unsigned. You don't do anything special to it. So let's go back to our imaginary 4-bit type, because it's easy to work with 4 bits. So I showed you 2's complement. If I need to make 1001, which is -2, is it? No. No, it's not. It's -7. If I have -7 here, which is 1001, and I need to and I convert that to an unsigned type. So let's say this is let's make it an actual value. So that's -7. No, it's not. It's -127. -127, and that's stored in a char. Let's say unsigned char y equals x. That's just going to take x and assume that it's signed. So that goes from being -127 to being 129. That's super useful. But yeah, the C doesn't know what else to do with it, so it just assumes it's a different type. Could it get any worse? Yes, it can. But it can also get slightly better. So that's one case where C doesn't know what to do with it. But what C will generally try and do is try and make everything, as I said before, it generally works in words, but in the case of C, it will try and convert everything to an int, which is 4 bytes long. So we have our int, which is 4 bytes. So we have our char here. So say we have an unsigned char, but it tries to convert it to a signed int. So what happens if we go from unsigned to signed? Do we lose our sign like we would if, say, we went from 129 and just converted that straight into a signed char? No, so he's a bit smarter than that. Because all of the numbers that can be expressed, as we would say, with a signed an unsigned character, all the way up to 255, can fit inside the signed version of an int. Then we leave it as 129. So the int version of this would be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1. And we'd keep its value of 129. But what if this was an unsigned? What if this was a signed char and we actually wanted it to stay as the value negative 126? Well, in that case, we do what's called sign extension, and to make this an int, we just say, well, because that it's signed and that first one's a 1, we're going to make all the rest of these a 1. So we go 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Have I done too many? 1, 2, 3. Yeah, that's too many. Zero, 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 0, 0, 0, 1, or 0x, f, 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 8, 1. And so we do sign extension. And you say, oh, that's all hunky-dory. We can fit our unsigned types into our signed types. But what happens if I have a negative signed type and I put that into a much larger unsigned type? Do I lose the negative value then? And the answer is yes, and that's going to be a source of a lot of problems. It's pain for everyone. So the rules that C follows are as follows. First of all, we'll try and make everything at least as large as an int. So if you're using unsigned or signed chars or shorts, and they get converted to signed ints, that's fine. They still keep their value because ints can do that. If you have an unsigned int and you're trying to store your values inside the unsigned int, everything loses its sign and chaos happens. And anything that's larger or considered wider than an int, so an unsigned int, or a long int, or an unsigned long int, or a long long, or an unsigned long long, and the longest of all, the double and the float, we convert everything up to those as best we can. If they're signed, it's not so much of a problem. If they're unsigned, then we lose the signedness, because there's no way to keep it. You think, well, that's pretty straightforward if I'm storing stuff in a variable. How can I get tripped up by that? The answer is, when you have an arithmetic expression, so variable a plus variable b, or variable a plus constant, it tries to make everything in that small expression the same size, and it will go for whatever the largest is. So if you have variable a, which is an unsigned type, plus some constant which is negative, and it underflows, so it becomes some very large number, you may not see it coming because it may not be obvious in the code. But to summarize, we have these two lists. So everything in this first list, except for the unsigned int, gets broadened up to the size of an int for any arithmetic conversion, regardless of what types are involved. Even if they're both smaller than an int, they both get expanded to the size of an int, and they don't lose any information. Unsigned int, if there's an unsigned int involved, one of the two sides are an unsigned int, then everything becomes an unsigned int and you lose signedness. And then it just keeps going up from there, and it expands to both types to whatever the longest is. So it gets very tricky, and you have to watch out. So in light of all of this, I have prepared a challenge. If we exit this and we open up the challenge.c file, And I can assure you challenge.c won't raise any errors with wall or where. But if we nano challenge, there is 10 tests here that just do a simple comparison. What I want you to do is look at these 10 tests and on a piece of paper, write whether you think they're going to print true or whether they're going to print false, and and try and explain to yourself why they might do that. And then compile this program and run it and see whether or not you were right. I'm not going to compile and run it for you. That's something you have to do yourself. And then if you're wrong, you have to go back and try and figure out why you might have been wrong in any cases you were. But also try and make sure that when something happened the way you expected it to, it's because of what you expect. Sometimes you might be right with these, and you might be right for the wrong reasons. So be very careful with this challenge. It's a bit tricky, and there's some curveballs. And the last one, test 10, involves the size of function thing. And the reason that is there is if we go back to here, size of doesn't return an int, it returns the type size t, which for most 64-bit processors with Clang is going to be the same as a long unsigned type. And the important thing there is that it's unsigned, which means if you use it in any equation with any arithmetic with anything else, that whole expression will be in unsigned, and everything that will get converted to unsigned. And here's a program that I ran just to test that it was unsigned. And with unsigned comparisons, if you compare it, say such and such is less than 0, you will get a warning that that it makes no sense to compare less than 0. But that's the only time you'll get a warning with unsigned types. There may be cases where it's not so obvious that you're doing a fruitless comparison. So be very careful. And the other thing I mentioned previously was the Linux man page, or manual function, which you can use to look at different functions. So anyway, I hope that this session has been useful. If you have any questions, feel free to contact me on Twitter or on Open Learning. I'm just Curtis Miller. Fairly easy to find. And I look forward to running another session tomorrow on some more complex stuff. In the meantime, thanks for watching. Outro music plays.